Anyway, so, okay, what do you think? We had microfluidics yesterday. If we go nanofluidics, so instead of having micro scale channels, we go to nano scale channels. What do you think? What will be different? What do you expect?
Surface interactions.
Sorry?
Surface interactions.
Surface interactions, yeah. And can you give some names to that? Surface interactions, very general.
Electric interactions. Lots of more surface area, so the electric properties of the channels will be more important.
Yeah. So surface area. Surface interactions. And you already mentioned electrical. Okay, could you think of other things that would change if you make channels very small?
Maybe molecules don't act as a fluid anymore, but as particles.
Yeah. So you can say you could describe them as a particle flow. That's another theoretical description we might need, yes. Some more ideas? If we make our channels 10 nanometers, 5 nanometers.
Maybe pressures will become higher.
What do you mean?
Well, yeah.
We need a high pressure to pump things through. That's what we saw yesterday. Yes, that's true.
Yeah, okay.
But that's just scaling down. So. Okay, well, these are indeed some things that will happen. We'll have a look what other things might be happening. So, in general, people define nanofluidics as the study and applications of fluid flow in and around objects smaller than 100 nanometers. So they put the cutoff, let's say, at 100 nanometers. When you look at nanofluidics, then it's a relatively new discipline, but the name is new. It's actually quite old. We now have a separate discipline because we can do engineering in the clean room, so we can make devices which are very small. But previously, people were studying the same phenomena, for example, in, let me see, what is it, soil science, where between clays, the distances also are very small. Or in biophysics, for example, in the a lipid bilayer of cells, there are very small proteins, and in these proteins you find water channels. They are real, very small nanochannels. In polymer science or in colloid chemistry, people looked at interactions of particles that were maybe 10 nanometers big. In food science, you know, you have in milk, for example, little droplets have typically that size. So you would say that's also nanofluidics. So it's very old, but as an engineering discipline, it's new. Okay, because we got the clean room now. What will I talk about today? So overview, the forces that play a role on the nanoscale. How does liquid flow proceed on the nanoscale? We look at electroosmotic and pressure different flow. And then we look at separations using structures that have nanoscale dimensions. And we'll see that steric, entropic, and the electrostatic effects will play a role. And finally we look how we can deal with the very low quantities of analyte that we get when we have very small channels. Not much fits into it actually. So is it anything special, the nanodomain? Yes, it is. So if you get structures, let's say, smaller than 100 nanometers, HIV, for example, won't fit in. It's too big. Ribosomes will fit in, but there's not much space left. Nanochannels, for example, could even be smaller than albumin, which is the protein that occurs most in blood. And if you make very small ones, you'll even have trouble getting water in. We'll see that, an example of that later. So yes, it's special because your structures become of the size of proteins, molecules. And I already told you, like, okay, nanofluidics has been around for a long time, and people have actually, one of the devices with which they studied the behavior of liquid on a very small scale was the surface forces apparatus. So it's a block. In the block you find liquid, and in the liquid there were two crossed cylinders that you see there. So they were, one cylinder was like that, the other one was like that, and they brought them closer and closer together, and they measured the force that was needed to bring them closer together. And at the same time they measured very precisely the distance. You So they could find the force distance curve. So they could find out how these surfaces would repel each other when they brought them closer together. They used mica for that in that case because mica by cleavage can be made atomically flat. So you have two very flat surfaces, so you don't need to think about roughness. Now, at the smallest scale, they found, so here we find either repulsion or attraction between the two surfaces. Then they found repulsion, positive numbers, but it went like oscillating. So what was happening? So at some distances there was a lot of force needed to push the two surfaces closer together, and suddenly then it was easy. And then people said, okay, we'll be pushing away layer after layer of molecules in between these two cross cylinders. And so you can really find out here about the structure of water layers in between two surfaces when they get very, very close. And people found that actually the layers closest to the surfaces, they're very tightly bound. These are solvation forces. Hydrogen bonding, for example, van der Waals forces at a very short distance. And of course, when you got molecules of a different shape, this curve will look differently. So this was for water. Okay, so these are solvation forces in the case of water, hydration forces, and they're very strong. And here actually people took a bigger molecule, about 1 nanometer large, and they pushed them away in layer after layer. And in the next slide you can see a movie of this. And this is actually a transition of 4 to 3 layers using interferometry again. You can see how in between these two cross cylinders water kind of from the middle, or not water, this molecule moves out. One single layer of these molecules move out in between the two cross cylinders and bring them closer together. So you can study, for example, friction on these very small scales. So these solvation or hydration forces, they are based on electron pair accepting or donating forces, which can, for example, be hydrogen bonding. They're very strong, about 10 times more than the van der Waals force, and they decay exponentially in water with a characteristic length of about 1 nanometer. So you find them only when things are very close. These forces extend into the liquids about 1 nanometer, not much more. Then you got van der Waals forces. Now van der Waals forces are based on polarization of your molecules or atoms that they can get because the electrons are not always equally distributed around the nucleus. So you can have delta plus, delta minus around your atom or molecule. When you got 2 of them, the delta plus, delta minuses can cause delta pluses, delta minuses, induce them in the other cloud of electrons. So you get attraction, let's say, almost from nothing. And if you've got very big electron clouds, these van der Waals forces can be quite appreciable. Now, that is van der Waals forces that are based just on the distributions of electrons that can come about by chance. But also, when you got a fixed dipole, it can induce a dipole in an electron cloud of another molecule. That's another type of van der Waals force. And of course, you can also have dipole-dipole attraction. When you've got 2 dipoles, they directly attract. So these are different classes of van der Waals forces. And when people bring these cross cylinders together, you can see an attraction here, negative signs for the force. And for these 2 cross cylinders, they found these van der Waals forces sticking out about, well, up to 5 nanometers to the solution. It's actually between the sphere and the surface, that is the force. So here we got the radius. So that's the radius of the sphere. So the force is proportional to the radius of the sphere and inversely proportional to the square of the distance in that case. Right, so these are van der Waals forces a bit further than the hydration forces, about 5 nanometers. There you can still already feel them. Then when we go further away, and here you see a distance up to 50 or 100 nanometers, you can feel electrostatic forces. Now these 2 mica surfaces, they have the same charge, so they repel each other. When you try to bring them close together, they would repel each other. And you see this is a 10 to the minus 4 molar potassium nitrate. And you find a strong repulsion up to almost 100 nanometers. When they increased the salt concentration to 10 to the minus 1 molar, they didn't find the repulsion anymore. They only found van der Waals forces, attraction. Would you know why? Would you have an idea why, if you increase the salt concentration, the electrical forces start disappearing at such a large distance? Would you know? If you think about the electrical double layer that we briefly discussed yesterday.
The ions start shielding the effect.
Precise. So when you have a lot of ions, there are lots of ions available to shield the surface charge of your mica, so they can sit very close to the surface. And that's what you see in the next slide. You already are familiar with this picture. I showed that to you yesterday. That's our electrical double layer. You know, you find on the inside of your beer glass, minus 50 millivolts. Now, this potential decay is dependent on the amount of counter ions that are present in the diffuse double layer. And when you calculate it with simple approximations, then you find that this potential profile as a function of distance from the surface has an exponential decay. So it's equal to the Z potential times the exponential of the distance divided by the Debye length. The Debye length, therefore, is the characteristic length of this exponential decay. So if the distance y is 1 Debye length, we got e to the minus 1 here. So we have about 30% or something left of our original Z potential. So, and how big is this Debye length? Well, the Debye length, people find out, depends on the ionic concentration. And when the ionic concentration is 10 to the minus 4 molar, there are not many ions present to shield it, and this potential extends to about 30 nanometers into the solution. So at 30 nanometers distance, or if you have two surfaces at 60 nanometer distance, you already find repulsion. If you decrease the ionic concentration more, it even becomes 100 nanometers. So it goes with the square root of the concentration over here. However, at 0.1 molar, the Debye length is only 1 nanometer. So you don't feel it anymore. You start feeling the van der Waals forces first, because there is all these shielding ions, they're really close to the surface. So the potential already becomes almost 0 at 1 nanometer of the surface. So these electrical forces are quite interesting because you can play with it. It's a function of concentration of the ions. And they are actually normally the dominating forces in nanochannels. And then you've got something that comes from the French school of investigation. So the French have always been good at colloid chemistry. And they found that if you make hairy surfaces and you try to bring in the surface forces apparatus hairy surfaces close together, so you have some macromolecules sitting on it that can act as a kind of springs, and you want to bring them close together, you find that you have to compress these molecules. And depending on the molecular weight, a small one or the large ones, you can find these repulsive forces quite far, up to 100 nanometers into the solution. So the size of molecules that are in your nanochannel will also make a difference. And actually big ones, you won't be able to get them in, of course. Not as a ball of wool, because they won't fit in there. So you probably have to stretch them in order to fit them in. And we'll see that for DNA later. Anyway, in the surface forces separated, we find this, they call it fluctuation forces of repulsive molecules attached to the wall. So in the nano domain, from the surface forces apparatus, we know now a lot of forces. We know solvation forces, solvent sticking to the wall, very short distances, 1 nanometer. Van der Waals forces, they extend to about 5 nanometers. But van der Waals forces, actually, it's just attraction. They're only attractive. But if I've got a solvent that is attracted stronger to the wall than my solute, then actually my solute will be pushed away because the solvent wants to go in between. So then it's a repulsive force for my solute. Actually, it's only an attractive force for everything, but it attracts more that one than me. So I will be repelled. So they can work in two ways, van der Waals forces. Electrostatic forces can be attractive or repulsive, depending on the sign. And they can extend really far. And these fluctuation forces are strongly repulsive. It depends on the molecular size. Okay, that was looking at the surface forces separation. So we have an idea now about the forces that we will have to deal with in nanochannels. Now what about the fluid mechanics? And it was already mentioned, we might be thinking of separate particles. And that's actually true. So if you got, and this is for sand, if you got 10 to the power 15 grains of sand, you cannot use, with any computer, you cannot do like a billiard ball approach anymore, you know, because the physics would become too complicated. But you can just describe it with like a generalized force, you know, it becomes like a liquid with some liquid properties like viscosity, which are bulk properties. So you describe then the system with bulk properties. And that's what we normally do with water. We say water has a certain viscosity, certain density. And we're not describing the water as a single molecule. But if we go down to a system where there are just a few water molecules, we need to go to the billiard ball approach in order to describe the system. Because we'll be able to count separate water molecules. And that's what people actually do. So then they start doing molecular dynamics simulations. So they describe the system as separate particles. And they model the ensemble of separate particles. Whenever the system is smaller than about 2 nanometers for water resistance, you would normally say you would do molecular dynamic simulations. And what they then use is well, one of the things you can use is a Leonard-Jones potential. So that there are 2 forces then between 2 molecules, an attractive one and a repulsive one. And the repulsive one works at very short distances, and the attractive one at longer distances. That means you get a minimum at some approach between the 2. So one can be van der Waals, for example, and the other one can be the repulsive forces of the electron clouds. So you can't have 2 electron clouds overlapping. So you find an optimum. That's one way of modeling your liquids. If you have water, you will have a dipole in there as well, or hydrogen one. Okay, so that's a little bit, teeny little bit about description. Now we go to electrosmotic flow in nanochannels. So yesterday we saw the electrosmotic flow in microchannels, as you remember. Can you still remember some of the characteristics of electrosmotic flow in microchannels? One thing?
Flat velocity profile.
Sorry?
There would be a flat velocity profile.
A flat velocity profile, so plug flow, because you moved only the ions very close to the wall. Can you remember anything else? So what about a scaling? If we made our channel smaller, what happened to pressure-driven flow? Do you remember? If I made a channel 10 times smaller and I applied the same pressure, what would be the flow, the volume of the flow velocity? Would it become 10 times smaller? 100 times smaller, yes. So it's scaled with the square of the diameter of my channel. And with electrosmotic flow, remember?
Stays the same.
Stays the same, yes, because the charge density at the balls, when that doesn't change, you have the same velocity. Okay, now what about nanochannels? Does it still hold? And actually, no, it doesn't hold when we make our channels really small. Because this is a microchannel, and what we see here is electrical potential, so you only find it very close to the wall. You find a potential which is not equal to 0. The bulk, you find just as much positive as negative ions. Okay, there is no space charge, there is no electrical, there's no field here. And as a function of the distance, these are the positive ions and these are the negative ions. Negative ions are almost 0 close to the wall. Positive ions are the counter ions that are attracted to the wall to shield charge. So this is the 2 distributions of ions. If I bring them closer together, at one point, these 2 potentials start overlap. And the whole channel becomes, the whole liquid becomes positively charged. And now, I find in the entire channel cross-section, I find only positive ions. And just a little bit of negative ions. There's a little bit of co-ions, as you call the ions with the same sign as the wall. And almost exclusively counter ions in the channel. So no electroneutral bulk anymore. Everything becomes charged inside the channel. Now, and that makes a difference to the electrosmotic flow. So you remember, we had this term here, in our Navier-Stokes equations. This is the pressure gradient. That was this electrical body force. Yeah? Now this electrical body force will now work across the entire cross-section of the channel. So And this is our equation that we will have for our electrosmotic flow, of course. That's also true for microchannels. Now, how to calculate the electrosmotic flow profile? Now, this is our Navier-Stokes equations. That's what that we derived yesterday, with the electrical body force. Now, here is the charge density. And there is something you can write from your electrostatics lesson, so the electrical engineers among you will know this. That's Poisson's law. And Poisson's law relates the second derivative of the electrical potential, so it's the first derivative of the electrical field, so the gradient of the field, relates it to the charge density. You can look it up in your books. Anyway, this is the relationship, Poisson's law gives this, between charge density and the electrical field, the local electrical field. And this is your dielectric constant of the solution. Now, if I insert this equation into that one, I get this equation. So the second spatial derivative of the velocity times the viscosity is equal to the second spatial derivative of the potential times the permittivity times the electrical field. That's nice, because I can just integrate this guy twice, and I have the solution. So this is extremely convenient, because the two depend on the same, in the same way, on space, on y. So, using these boundary conditions, you can check it as this at home, then you get a very simple solution, for example, for a slit. So just two plates that you bring close together. And then you see here that the velocity profile is a function of distance from the wall, that's the y coordinate. It's the same shape as the potential profile. But that's logical, because they both depend, or their gradients depend on y in the same way. Now, that means that if we know the potential profile, and we can calculate that with the electrical models, we will know the velocity profile. Okay, now for any geometry, we can calculate the potential profile. That means for any geometry, we can now calculate the velocity profile. For a tube, or for a slit type geometry, or for a square, or whatever. Very convenient. So, now, if our radius, for example, of the channel is much larger than the Debye length, then we go back to the microchannel. So we have a very large one, and the Debye length is only very close to the wall. That's the microchannel situation. Then the potential is 0 for almost all y. Only very close to the wall, the potential is not 0. Then we get the same expression as we had yesterday for microchannels. This is this Helmholtz-Smoluchowski equation that you remember. So basically, everywhere, this psi is equal to 0, so it falls out, and you get that equation. However, when you go to nanochannels, it's different. So the red one here, I put it in comparison for microchannels. And then you see with microchannels, the velocity is high everywhere in the channel. So this, let's say, would be the velocity. Yes? So the velocity is 0 here, at 1 there. And this is normalized. So let's say they always divide by the radius of the channel. So, and that's why you can put all these curves on top of each other. Now, this one is when the height of the channel, I guess the half height in this case, divided by the Debye length is equal to 2. So we have strongly overlapping double layers there. And then you see that our flow rate is smaller, a lot smaller than in the case of a microchannel. So we have our electrosmotic flow becomes smaller when we bring the two surfaces closer together. And it's not anymore a plug flow, it's a parabolic flow. Now how can we understand that? Well, if you bring the two channel walls closer and closer together, you're pushing out the counter ions. And actually you get a lot of charge on the walls which is not shielded. So that means there are just less counter ions, so I can exert less force on the liquid. So my flow velocity will become smaller. Yeah. also, everywhere in the channel cross-section there are now ions. So, and then it becomes like the force, I will exert it everywhere across the cross-section. And then it's just like pressure-driven flow. You know, with pressure-driven flow, you exert the force everywhere in your channel, and you get a parabolic flow profile. Now here, there is charge everywhere in the channel. I have my electric field everywhere in the channel that are in the axial direction. So everywhere I'm pushing the liquid. And then you remember, then you get this parabolic flow profile. And here we get it as well. But it's smaller, because there are less counter ions in our channel. So, only when height over, I have to check this whether this is height or half height, so that's the journal, you can look it up yourself as well, I forgot. But only when it becomes like 8 or 10, then we almost reach the maximum velocity in the center. But even then, we won't have a flood profile. So in nanochannels, two things. The electrosmotic flow is suppressed, and it becomes parabolic. Now what about pressure-driven flow? Well, you remember from yesterday that the average velocity of the pressure-driven flow scaled for a slit type channel is scaled with height squared. Remember, so you make it 10 times smaller. Pressure-driven flow velocity is 100 times smaller. Now, that's nasty. So, for example, you need 100 bar to pump at an average flow velocity of 1 millimeter per second through a nanochannel of 100 nanometer height and 1 centimeter length. So that's a lot. And it's only 1 centimeter long. Often you want to use 10 centimeter. And then, of course, you would need 1,000 bar. That's almost impossible, you know? And connecting 1,000 bar, for example, you need really strong connectors, which normally won't work. People who do the experiments know this. They will break, or something will explode, or whatever. So, what to do about this? Now, one of the things you can do about it, and people have discovered this, and you will see more examples later, is liquid slip. And that's again the French, who were really smart engineers around the time of Napoleon, you know, that's when he started. So they had these big armies marching through Europe, the boss, and these big armies, they needed engineers because you needed to build bridges, you needed to have these cannons or whatever, you know, and engineers became really important. And Navier was one of them. And so Navier said, and of course people didn't know, so if I push liquid through a tube, is the velocity at the wall 0? Now we think, yeah, the velocity at the wall is 0, you know. I say it because everybody says it. Is it true? You've got to do experiments. And there was one guy, Girard, he said, I do experiments and I think the velocity at the wall is not 0. And so Navier, who was a good mathematician, started thinking, okay, what if the velocity is not 0? What will happen? And so he made this Navier boundary condition. People still use it. And they say the velocity, so this is the y, normal to the wall, coordinate, at y is 0, so the velocity at the wall might be not 0. And we might say, and he says, okay, that's slip, that this is parabolic flow, but at the wall actually the velocity is not 0, but is kind of some finite value. And he says, okay, then I take the gradient of the velocity at the wall, and I take the tangent to it, and look where it intersects the velocity is 0 line. And that length that I then get, I call it the slip length. Okay, just a question of definition. So he said, okay, well the velocity at y is 0 is the slip length times the gradient of the velocity, that is this Navier boundary condition. So then the slip length will define the amount of slip. So if the slip length becomes larger, you know, this guy moves more and more to large values. There's more and more slip. And this can, for example, happen if the solvent molecules do not really like the wall molecules. If you've got water and you've got a lipophilic wall, fatty wall, there is not much attraction between the water molecules and the wall. And they might just want to slip. There might actually be a little layer of water, of gas. So they just have no affinity. Then they can easily slip. Now, so let's say there is totally no affinity of the liquid molecules with the wall. No affinity at all. I would exert a force, for example, by a pressure. If there is no friction there, what would happen if I exert a force on the water? There's no friction at all.
No
with the
movement.
No gradient, no velocity gradient.
Yes.
So it stays the
And
same.
so if I exert a force, what would happen to my liquid?
It's moving in a straight line. Down
It
the
moves in a straight line, yes.
Yeah.
And what will the velocity be?
The same size as the center. Yes.
Yeah, but if I keep on exerting a force,
Goes to infinity.
yeah, it will increase. F is m times a, isn't it? So I'll get a particle accelerator.
Acceleration.
I was just exert a force, it will go faster and faster and faster and faster. And nothing, there was no friction anymore, because if there's no internal friction in water, why would it? Because I hold it at no place. It would go, so that's interesting. So pure slip never will exist. And you will get turbulence in some point if there is a little constriction or a little, you need to make a turn or something like that, you know. So that's also what you need to do with particle accelerators, because things want to go straight, so you have to go to sideways force. Anyway, so no slip, partial slip, perfect slip. So perfect slip we never have, but what happens to our average velocity? Well, if you integrate the things with the different boundary conditions, you find there's an extra term for your average velocity. And this is the one that is added. If the slip length is 0, it's just 1. But if the slip length is not 0, we get a velocity which is higher by 6 times the slip length of the height of the channel. Now, that means if the slip length is of the order of magnitude of the channel, then I will have 7 times as much flow as I have when it's not the case. So that's a big effect. And the slip length, people have found slip lengths which could be in the order of maybe 20 nanometers. So for very small channels, you then get quite a lot of extra flow. So this is for nanochannels another approach. You can have electroscopic flow, but you can also have somehow start creating slip. Okay. Now I am about, I guess, 10 minutes behind. So what we can do, you can have a break anyway, and then you miss a few slides at the end, and you just read them yourself, or you can say we go on.
Let's go on. Go on.
Go on.
Go on?
Yep.
Right, okay, we go on. Now, sieves. If you things are really small, you can make molecular sieves. Now, and the first example I want to show you is a molecular sieve that actually biology is using a lot. And they are aquaporins. So the word already says it is water and pore. And cells in roots of trees or leaves of trees or our kidneys or our eyes and many others, they use these aquaporins in order to regulate the water pressure inside themselves. And you find them all through nature, in all the kingdoms, animal and vegetable kingdoms. And if you look at the scales that I mentioned in the beginning, we are now really at a smaller scale, so where you find aquaporins or carbon nanotubes. So they are about the size of water molecules, 0.3 nanometers. And these are aquaporins. So here the yellow stuff is the lipid bilayer. So it runs from here to here, and the aquaporin sticks through the lipid bilayer. And it has 4 units here, and in the middle of these 4 units you find a little channel. That's where water can pass. And they conduct, therefore, a little layer of, or little single file of water molecules. This is a model of how it more or less would look like. And water will move from high potential, for example, high pressure, to low potential or low pressure, or from low salt concentration to high salt concentration by osmosis. Now, you see here that at the top, this part of the channel, the hydrogen atoms stick up. So the hydrogen bonding is from the oxygen electron, what do you call this thing? Electron orbital to the hydrogen of the other water molecule. So here they're sticking up. And on this side, they're sticking down, as you can see. So there is a change of directionality of the water molecules. Now, it's caused by these 2 positive charges in our aquaporin. So they're amino acids over there, and their function is very important, and I'll show you why. So they block proton transport. Now, Would anybody know why our cells would like to block proton transport?
So you keep the acidity at the right level?
Yes, that's one. And if you transport a proton, are they charged? If a 1 plus charge, so what happens if there is free charge transport through a cell membrane?
Potential difference.
Yeah, well, actually, but there is, yeah, normally cells have a potential difference.
Yeah.
And they work very hard to keep the potential difference there.
Yeah.
So, and what if their ions can just move through the cell wall? Yes, you will die. Because the potential difference disappears.
Yeah.
And cells depend on it. They work hard to have it. So, when cells contain aquaporins, they can't have aquaporins that just conduct protons, you know. You might be able to have a very small one that won't let sodium ions through, because sodium ions always are coordinated with water molecules. They're too big to pass through it. But protons could pass through it, just attached to water molecules. So you don't want it. Now, they do that by this orientation. And so normally protons can move through water by the so-called Groth-Hus proton conduction. So they are like firemen that pass buckets, let's say. In the bucket that is the proton. And if you've got a fireman, you can pass the bucket. So from one to another. Water doesn't need to move. The H3O plus doesn't need to move. The protons move on the back of the water molecules. Now, that is impossible if they have they are oriented up and down in two places. So they can't pass in the middle, the bucket. So this Groth-Hus proton conduction process is impossible in our aquaporins. And that's why these amino acids here in the middle. Now that's really, really, really smart of nature, you know. And this is the type of thing we would like to do in the clean room in the end, somehow, you know. Have things on such a small scale that we actually can, on the nano scale or on the sub-nanometer scale, can control the behavior. Okay. And this is an animation of water molecules passing through an aquaporin. It's actually not an animation, it's a molecular dynamic simulation. And you can follow this yellow one. So they made one yellow so you can easily follow it. You see how in time so these are your two amino acids. So in time it wriggles itself away. So this is thermal motion that you see here. So it's 1 nanosecond out of the life of aquaporin. And here you see all the protons, or all the H plus oriented upward, and here you see them oriented downward. And you see there's a very small constriction, and the water is just in a single file here through the aquaporin. Now, there are other sub-nano channels. But that's our aquaporin with 0.3 nanometer. This is a carbon nanotube. And also in a carbon nanotube, you can have, if there's a small carbon nanotube, you have them all kinds of different sizes. You can fit in a single file of water molecules. We'll see a little bit about it later, but they're very conductive to water. And these are two other ones. Tubes, 0.3 nanometer, 0.7 nanometer. Now this is a gramicidin, is an antibiotic. If I remember well, it's made by fungi in order to kill bacteria. And what happens, so it inserts itself in the lipid bilayer of the bacteria. And this one is permeable to ions. So bacteria gets leaky, it gets killed. This is a synthetic, this is a man-made one. And it's octapeptide, so they made circles of octapeptides, and they can self-assemble by hydrogen bonding. And they can self-assemble themselves in the wall of a bacterium. So if you give this, they gave it to bacteria, bacteria died, because they self-assemble themselves in their lipid bilayers. It became a pore, a tube, sticking through the wall, like somebody putting a tube in your heart, you know, blood of that endobacterium. Now, so, and I didn't see much of it anymore, so probably it was toxic for humans as well, I don't know. Anyway, but the idea was great, you know, making something which is really, 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 really small and has a physics behavior in consumption. And quite soon people start trying to get these carbon nanotubes into membranes because they hoped that the conduction to water would be much higher than of other channels, and indeed they found that. So they found slip lengths of about 50 micrometer, they said, which is really large because normally you would only get nanometers. They think now it has to do with the curvature of the carbon nanotubes, so which somehow is such that there is very little interaction between the water and the carbon nanotube. Water, of course, holds hands, hydrogen bonding, and then water moves through it in a single file, so it can easily go out of the door and almost no just interaction of the water with the water, not of the water with the carbon nanotube. So now later I show you a desalination membrane where they actually use carbon nanotubes in order to have high flow rates of water. So these carbon nanotubes are, from a fluid physics point of view, very interesting things. And they look a little bit like these aquaporids, only not function-wise. Now, so the aquaporids work as a sieve for protons. It's a sieve, they don't let protons pass, they let water pass. So what about nanotechnology to sieve other analytes? Huh? Can we make small sieves for other things? Now what is a sieve? Now, if you generalize it a lot, you've got a simple sieve you use in the kitchen, you know, big things don't pass, small things go through. And everything goes in one direction. But you can have sieves in different ways. You can have a microscopic force field, for example, hydrodynamic flow or electrical field that exerts a force. But on the blue one and the red one behave differently under the influence of this force. This red one goes fast with the force. The blue one goes less fast and kind of at a tangent to the force. That can have to do with the fact of the structuring of this sieving matrix. So the sieving matrix can do things. It can push things in one direction or other direction. It can stop things going in one direction at all. So interesting stuff. Sieving matrices, and we can nano-machine them. So in all cases, the flux is equal to the concentration times the velocity. We saw that already yesterday. Mole per cubic meter, meter per second, mole per square meter per second. Now, how can you sieve? One very simple one. In the beginning, I asked you, so what's different in nanochannels? And it was said, yeah, there are interactions with the surface. Well, a very simple interaction is the interaction that something can't get closer to the wall than its electron cloud will allow. That means that the center of a sphere with radius r can't get any closer than r to the wall. That means that over here I will find the concentration 0. Only over here I will find the bulk concentration, if that's the only interaction with the wall we have. Of course we got also the electrical one, but if that's the only interaction, just the hard sphere repulsion, I will find an average lower concentration in my channel than in the bulk. If I got a large sphere, actually one of that size, the concentration will actually be 0 at some moment in time. It will be 0 flux, it doesn't fit in. Okay, so average concentration in this case is the bulk concentration times height minus radius divided by radius. It's just that squared divided by that squared. So the particle flux will be decreased due to this hard sphere repulsion. Things only fit in the middle of the channel, or not at all. Another factor is entropy. So what do we have here? Well, we have a DNA molecule that we stretched. You can stretch DNA molecule by attaching it to a surface, for example, have hydrodynamic flow. It will be pulled apart like a fly trap, and then you can leave it to itself to relax. So they stop the flow, and then they make every 2.5 seconds make a picture. And then finally the DNA gets back to a little ball. How come? Well, because the DNA wants to, the different parts of the DNA, you know, all the locations along its strand, will diffuse freely. And it will go to some average conformation. And average conformation actually is something like a sphere. Because there are so many conformations that look more or less like a sphere, that one will always win over the single one, which is an extended strand. So that one is really improbable. There's only one of it. Well, like the blob, there are 10 to the power, I don't know how many of the blob. So in the end it will be like a blob. So it doesn't want to be like that one. And you need energy, entropic energy. You need work against chaos in order to make that one. So that's another way of sieving, because if this one doesn't fit, and the DNA needs to become like that one in order to pass through my channel, it will be an energy barrier. And that's what you see here. So, to move DNA through a pore, there's an entropic energy barrier. The moment it's here, the energy is, it costs energy. Once it's through, you win the energy back.